So we were talking about relaxation. We were talking about what happens when you stop a radiofrequency pulse and protons slowly realign into B0. And we said, as they do this, there are two aspects to relaxation. One is about dephasing. It's about protons losing coherence in the XY plane, or T2 relaxation. And one is about recovery of the projection on the Z-axis. So it's about protons realigning back into the field and going back to pointing up straight into B0. Now, as we discussed a little while back, I had said that the beauty of T1 and T2 in terms of the properties of different tissues is that you can adapt the way in which you take a picture with MRI so that you can see, so that you can get certain types of contrast, so that in the picture you can see certain tissues more than others, or certain things more than others. And I'll give you some examples in just a moment. So when we say, well, let's adapt the image we're taking, we're really referring to two key parameters of MR images, two settings. And one is known as TR, or the repetition time. And the repetition time is how long do you wait after one radiofrequency pulse before injecting the next one. In other words, really what this is saying is, given how long it takes for protons to come back into B0, how long are you going to let them relax longitudinally before you hit them again with another radiofrequency pulse? So in this sense, TR relates to the constant T1. TR relates, and I'll show what I mean in the next slide, to how long it takes for different tissues to relax longitudinally. And the reason why this is important is because you can only stimulate effectively a proton if they have relaxed enough in the longitudinal direction. So in order for your radiofrequency pulse to excite a proton, it must have come back up enough that you can hit them. Okay? If they haven't come back up enough in the Z-axis, the radiofrequency pulse won't be effective at exciting those protons. Now, the second parameter of interest, which instead relates to T2 relaxation, or relaxation in the XY plane, is known as the echo time. And this parameter really is asking, how long do you wait after the radiofrequency pulse before you capture a picture, or before you listen to, as it is called, the echo? In a sense, what this is doing is, remember the video where I showed you the XY plane from above, and you were seeing the M0 turning, M0 spinning and shrinking and getting smaller and smaller. TE is saying, how long are you going to wait after the radiofrequency pulse before you see how big M0 is in the XY plane? So in the sense, TE is really saying, how long are you going to allow protons to dephase before you capture a picture, right? So again, imagine that video, the one on the blue background. How long are you going to wait for protons to spin and therefore dephase and lose coherence before you see, you measure how big is M0? Now this, as I said earlier, relates to T2. Now let me give you an example of how this works, okay? So let's say we're going to start with our protons nicely, so with M0 fully relaxed. So M0 is really straight into B0, as you can see in the illustration up here. So the yellow arrow, as usual, is M0. The big blue arrow is B0, the magnetic field generated by the MRI machine. So, and then indeed, what I'm showing in these two graphs, MZ is how big is the projection of M0 on the longitudinal axis, so on the z-axis. And mxy is saying how big is the projection of m0 on the transversal plane. So here we are. m0 is straight up. How big is its projection on the z-axis? Well, as big as it's ever going to be, right? It's fully straight, fully up. So really, it's 100%. How about the projection on the xy plane? How big is that? Well, nil, right? There isn't any. It's 0. Now, here's what we're going to do. Now we're going to inject a radiofrequency pulse. What is going to happen to m0? Well, as you remember from the videos I showed you, it will nutate down into the xy or the transverse plane. So what happens once it's down here? How big is the projection of m0 on the z-axis? Nil, right? So the projection now goes down to 0, right? Down to 0%. On the other hand, how big is the projection of m0 on the xy plane, on the transversal plane? Well, as soon as the radiofrequency pulse is ended, it's 100%. It's as big as it's ever going to be, right? m0 is fully into xy, into the transversal plane. Then we stop the radiofrequency pulse. What's going to happen? Remember, we're going to have T1 and T2 relaxation. Let's start with T2 relaxation. By the way, these lines right here, you will see 3 different lines. The colors map on different tissues of the brain. Remember, different tissues of the brain have different relaxation times. So I'm going to picture that here. Okay, so we were in B0, m0 was in B0, radiofrequency pulse, and now m0 is fully into the transversal plane. Now we stop the radiofrequency pulse. What happens? Let's look at T2 relaxation first. Protons slowly dephase, right? And as they dephase, the magnitude of m0 on xy goes to 0. And that's what you're seeing these lines, right? Radiofrequency pulse, the protons are spinning all together, so m0 is the projection of m0 on xy is very strong. And then we let go of the radiofrequency pulse. Protons keep spinning, they slowly dephase, right? They start pointing in different parts of the phase with respect to each other. And as that happens, the magnitude of the projection of m0 on xy shrinks. And that's what you're seeing here. So we're 100%. For example, let's look at protons in the CSF, in the cerebrospinal fluid. 100%, you stop the radiofrequency pulse, the protons slowly dephase. And so the magnitude of the projection of m0 on mxy, on the transversal plane, shrinks down to 0. And the same is true for the brain. So putting together white matter and gray matter, just they dephase faster inside the brain tissue. And in fact, protons inside fat dephase even faster. Now, here's the last trick to keep in mind. The magnitude of mxy, is what we code in the brightness of the pictures of the brain. Let me show you what I mean. So first, let's set our TE. Let's say that our TE will be, let's see, what is it? 400 milliseconds, okay? So remember, TE is saying, how long are you going to let the protons dephase before you snap a picture? Or, in other words, before you listen to the echo of the protons, which means before you measure how big the projection of m0 is on the xy plane. Okay, so let's say we wait this long. So let's put a line right here. So CSF will be the intensity, the strength of the echo in CSF will be this much. How about the strength of the echo in brain and fat? Well, see, the protons, by the time we take the picture, have almost entirely dephased. So both in brain and in fat. So the bigger this number, the bigger the projection on XY, the brighter and the stronger the echo. Remember? So the more we let it dephase, the weaker it becomes. So how's this image going to look? How do you think this image is going to look? Well, CSF will be, a little bright. Brain and fat would probably be pretty dark. So if you were to do this on a slice of brain, the picture would look like this. See CSF, you can see it right in here. That and this is cerebrospinal fluid. And also some of the brightness that you see in here is cerebrospinal fluid. So cerebrospinal fluid is certainly the brightest thing in this image. Brain, which is sort of both the white matter and the gray matter, definitely darker. And fat, it's out here, it's kind of even hard to see. So by comparison, let me show you, if instead we took our TE here, how would you imagine the picture be? Would it be darker or brighter? So if we snap the picture or listen to the echo of M0, if we didn't let protons dephase this much, would the values be higher or lower? Well, let's find out. So let's say that instead of this TE, we do a TE this short. So we don't let protons dephase much, we snap a picture right away. Okay. How do you imagine this picture would be? Well, let's see. CSF would be pretty bright, right? At this point in time, the protons in CSF have dephased a little bit, but many of them are still in phase, which means that the signal would be pretty strong. In terms of images, it means that the little voxels inside CSF would probably be pretty bright. Brain would have dephased a little more, but would still be pretty bright. And the same is true for fat, compared to the previous image. So remember the previous image? Here, I'll show it again. Everything's pretty dark. Now, because we've waited too long and we've let protons dephase too much, so the strength of M0 projected on XY in the transversal plane was very little. But now we don't wait that much. We don't wait for protons to dephase that much. Our image overall, how do you imagine it to be? Much brighter, right? And that's exactly what we see. Again, CSF right here, very, very bright, very white. And you can see it down here too. These are the lateral ventricles, if you're not familiar with neuroanatomy. And I should say, I'll probably have a lecture on neuroanatomy for those of you who are not familiar with it. Brain, which is the second, the brown line right here. See, it's much brighter than before. Part of it is white matter, which is a little darker, and part of it is gray matter, which is a little brighter. And finally, fat out here, you can see it. It's pretty bright, right? So if we wait too long, protons dephase and we don't see anything, and the brain becomes very dark. We don't see, there's nothing to measure. The strength of the projection of M0 on XY, on the transversal plane, is really how intense, that is the number that we're capturing. And in pictures, we translate it in intensities. So the stronger the MXY, the brighter the pixel inside this image. Okay? So this is T2 relaxation as it relates to TE. Now, the other process that is happening at the same time, of course, is T1 relaxation. So not only protons are dephasing, are fanning out with respect to each other, T2, at the same time, they're also sort of wobbling back, they're realigning, right, with the magnetic field, with B0, T1 relaxation. And so if you look at the top graph, you're going to see that right after the radiofrequency pulse, there's zero projection on MZ because M0 is fully down in the transversal plane. But as we stop the radiofrequency pulse, protons inside different tissues will slowly wobble back up and realign with B0. Okay? And as I had said in a different segment, different tissues, just like for TE, tend to have different T1 values, which means the time it takes for them to realign with B0 is different. For example, in this graph, you can see that fat realigns very quickly. The protons inside fat tissue realign very quickly with B0, whereas the protons inside brain and inside CSF take longer. Now remember what was the other parameter, TR, the time of repetition? How long are we going to wait before the next radiofrequency pulse? So that is TR. So at this point, what we'll do is we would put in another radiofrequency pulse, and we would restart the whole process. As soon as we put in the radiofrequency pulse, boom, the vector goes, M0 goes from being fully in B0 to down in the transversal plane. So there's zero projection on Z. And it went from being down here, so zero projection in the transversal plane, to have full projection in the transversal plane. And off we go again. And then we take a picture somewhere, at T. And then after TR, boom, another radiofrequency pulse. And off we go again. All right. Now notice one thing, and this is why the TR is so important. Remember, I told you, so TE was how long do you let protons dephase before you listen to the echo, or before you snap a picture, as we would say, slightly improperly. TR is how long are you going to wait for protons to realign into B0 before you hit them again with another radiofrequency pulse. And I told you that if protons haven't come back enough, you won't be able to stimulate them effectively. And here you can see that protons inside fat have come back up fully. Protons inside brain, 2/3, and protons inside CSF, not that much. And indeed, in the second TR, when we're here, look at how we've stimulated differently protons in each tissue. All the protons in fat were stimulated and went into the transversal plane. Only 2/3 of the protons in brain were stimulated and went into the transversal plane. And really only maybe 1/3 of the protons in CSF were stimulated and went into the transversal plane. So you can set TR so to only get, for example, some types of protons and not others. For example, our TR here is pretty short. And as you can see, it really damages the CSF. So if you don't wait enough, you will not be able to stimulate protons in CSF, which means you won't be able to create an M0 in the transversal plane with the protons from CSF, which means you're not going to get much signal from CSF, or in other words, the voxels inside CSF will be pretty dark. Let me show this in practice, how we go from sort of these theoretical notions to pictures that look differently.